Hello. Now we are going to look at relative frequency and expected frequency. So relative frequency, which we'll call RF, just means the experimental probability. And what do I mean by that? If we run an experiment a whole bunch of times and we use that to get an idea of what the probability of an outcome is, that probability is called relative frequency. It's the frequency relative to how many times we ran the experiment. So frequency is how often we see something, and it's the frequency relative to our total. So our relative frequency is the number of times we got what we wanted, the number of successes that we had, divided by the total number of times we ran the experiment, or the trial is another name for an experiment. So this is simply wanted over total, what we already know for probability. The expected frequency, which we will often call capital E, is the probability of an outcome multiplied by the number of times we run the experiment. And both of these will become more concrete as we run into our examples. So for Health Week in a school, they want to buy fruit for every student. And so to know how much fruit to get of each type, they ask some of the students in a class what their favorite fruit is. So this is the result. So we have the 4 options of fruit that they decided to give, and we have the tally of how many students liked each type of fruit. So we're going to use this as a look at how tallies get written. So if we wanted to say the first student liked an apple, we'd put down one line for apple, and then another student liked an apple, another, and another. And then when we get to 5, we put a diagonal line across to say we now have a bundle of 5 students. And then the next student, we'd start with a next dash, and we'd keep filling up bundles of 5. And that's how this tally works. It's very convenient for counting up numbers, unlike writing normal numerals, which would be a nuisance if we had 1 student and then we'd have to cross 1 out and say we had 2 and cross that out and say we now had 3. The tally system allows us to count up our numbers very effectively in groups of 5. Now, this is the tally that we got from running our survey of our students. And we can translate this now that we've completed our survey into our frequency, how many students liked each type of fruit. So we have 5 and 1 is 6 students had a favorite fruit of apples. 5 and 5 is 10 and 2 is 12 students liked grapes best. 5 and 3 is 8 students liked bananas. And 4 students liked pears the best. So an obvious question and then might be, how many students were asked? How many students got given this survey of their favorite fruit? Well, 6 of them liked apples, 12 of them liked grapes, 8 of them liked bananas, and 4 of them liked pears. Assuming that everybody who was asked answered, that means that if we had 6 plus 12 plus 8 plus 4 people. So if we add up the frequencies, we have to get the total number of people who were asked. When we add all of them up, we get a total of 30 people or 30 students who were asked the question. So anytime we're asked this, we can simply tell ourselves the story of what this table is talking about. These are all of the people who were asked about their favorite fruit. So if I add up all of the different results, I have to get the total number of people that were asked. So if we can tell ourselves the story of what's given to us, we can often figure out these questions. Now, what's the probability of a student wanting an apple? In a question like this means what's the probability based on our experiment? So what are we really being asked for? We're being asked for the relative frequency. And they can be used interchangeably because we know that relative frequency is just experimental probability. So we're looking for the probability of an apple being the favorite fruit, or we could also say the relative frequency of an apple being the favorite fruit. We could write it either way, and the structure would be identical. We look for how many times we got what we wanted, our apple, out of our total, which we know is 30. And we can see there's a common factor of 6 top and bottom. So we can simplify our fraction. We could also just divide above and below by 6. That would be fine too. And we get a 5th as being our probability, and we always simplify our fraction. So again, we could write in a separate color or just write in next to it that we were dividing above and below by 6, or we could take out our common factor. Either will work, but we must show that we are simplifying and we must show how we are simplifying. So the relative frequency of a grape not being a student's favorite. So the relative frequency of not wanting a grape, of not having grape being the favorite fruit. Well, we could simply get all of the people who did not have grape as their first choice. So that'd be 6 plus 8 plus 4 all over 30. Those are all of the people who didn't pick grape, so people who picked apple, banana, and pear as their favorites. And when we add that up, we get 18 all over 30. And this time, and we'll do this another way. So here I took out the common factor. Here we'll just divide above and below by our highest common factor of 6. So we can divide above and below by 6. So this method is fine too. And we would get 3/5 as our answer. Now, there is another way to look at this question, and it's important that we think about it. If we think about our people who did not want grapes, if we think about all of our 30 students together, if we had the number of students who do not like grapes best plus the number of students who do like grapes best, that has to add up to 30. That has to add up to our total. Or put another way, the number of people who do not like grapes, rearrange the equation, would be, number of people who do not like grapes would be equal to the total minus the people who do like grapes. That must be true. We can say that in terms of probability or relative frequency as well. So the probability or relative frequency of not wanting a grape, that should be a G, would be equal, well, what's the total probability? The total probabilities always add up to 1 minus the probability or relative frequency of wanting a grape. So this is another way of looking at the same problem. So we could have 1 minus 8 out of 30. And when you work that through, you will also get 3/5. It's important that we can tell ourselves the story in both ways as much as possible, because sometimes this way of looking at it will be very, very useful to us. If there are 1,000 students in the school, how many apples would you expect to be eaten? So based on our survey that we did of our 30 students, how many apples would we expect to be eaten? Well, this tells me I'm looking for an expected frequency. How often would I expect the apples to be eaten? That's going to be the probability of a person wanting to eat the apple times the number of trials, the number of students. Every time we offer the fruit to a student, we're effectively running an experiment, a trial. So that is going to be E of A. So expected frequency of getting an apple is going to be the probability of getting an apple. Now we already got that. That's 1/5 times 1,000 students. So when we multiply that out, we will get 200 students. So we would expect that about 200 apples are going to be eaten if our survey is fairly accurate. Now, to the accuracy of our survey, how could we get a better idea of the probability of liking each fruit? Well, we only asked 30 people out of a population of 1,000. So how could we improve our accuracy? Well, we could have asked 100 of them instead. If we ask every student in the school, then we'd know exactly how much fruit we are going to need of each type, what the probability is for each type of fruit if we asked everybody. But it's impractical to ask everybody. So what we can do in general is just ask as many people as we can. If we ask more people, if we run the experiment more times, we'll get a better idea of the probability, so long as we're asking at random. So we want to ask more people, and we want to make sure it's a random sample. So ask more people, ask more students, and try to make sure or ensure that it's a random sample, that we aren't biasing the fruit that people would like by age or by gender. So let's have a look here. Testing a coin for bias. We flip a coin 10 times and 7 times we get heads. Well, that means the relative frequency would be 7 out of 10. Which we can convert, because we often like comparing these things, we can convert to a decimal and we get 0.7. Relative frequency after we've run the experiment 20 times would be 15 heads out of 20, which ends up being 0.75. Now at the moment, after 20 experiments, this looks like a pretty biased coin. 3/4 of the time I'm getting heads to show up on this coin. It looks very biased, but we keep running the experiments, and after 30 experiments we've only gotten 20 heads. That's going to be 20 out of 30, and when you simplify this, you get approximately 0.67. After we run the experiment 40 times, we got 24 heads, which works out to 0.6. And after we've run the experiment 100 times, we've gotten 53 heads. So that's a probability or relative frequency of 0.53. What's the probability of getting a head? Well, the only one of these answers that I'm interested in is the one where I've run the experiment the most times. There's no point in saying that the probability of getting a head is 0.7 after I only ran the experiment 10 times. I'm interested in this situation where I've run the experiment 100 times. That gives me a much better idea of the probability of getting ahead with this coin. So is the coin biased? I would say no. I would expect that the probability should be 0.5 or a half, and it is 0.53. That's pretty close. So I would say that it is not biased. If I flipped the coin at 2,000 times, how many heads would I expect? Would we expect? Well, that's an expected value problem. So the probability of getting ahead based on our experiments so far is 0.53 times 2,000. It's going to be 1,060, I think. Yep, 1,060. Next, we have a situation with a biased dice. We're just straight out told it's a biased dice this time, though we could see that from the probability of our outcomes. So we have a probability of getting a 1 is 15% or 0.15 and so on. So what's the probability of getting a 4? Well, I can see that information's missing here. But I know the probability of even a biased dice has to all add up to 1. At least one of these faces has to be landed on. So if I add 1.05 plus 0.24 plus 0.16 plus our unknown, which I'll call x, plus 0.1 plus 0.17. This all has to add up to 1. All of my probabilities have to add up to 1. So I add up all of my like terms. And I get 0.82 plus x. Must add up to 1. And rearranging that, subtracting 0.82 from both sides, I get x is equal to 0.18. Finally, this dice is thrown 100 times. How many 3s would I expect? Well, that's the expected frequency of getting a 3. Based on the information given, that's going to be probability of getting a 3 is 0.16 or 16% times 100. I multiply them and I would expect to get about 16 3s when I was rolling this dice 100 times. And that is what we need for relative frequency and expected frequency.